Today we are going to do section 4.7. We have first, let's look at the books. This has already been scanned before, okay? But for some reason I didn't mark it as scanned, so I'll just show it to you with some detail a little more. And then down here, that should do it. All right, next, page 146 and 47. Let's see, we will look at it like this. Okay, a little closer. Maybe move this direction, because that one corner seems maybe too much. Okay, that's close enough. And a little bit closer on top. And a little bit closer on the bottom. Okay. Next, page 148 and 149. Here it is. All right. Let's pull back a little bit. That looks tolerable. Okay. And then let's see, a little bit zooming in closer on top. And on the bottom, there's not much on this page on the bottom. That should do it. Now, before we start, I want to show you this definition of a cylinder real quick, okay? Because you're going to need it in the homework. And I'll talk about it later, but I want to show it to you in case I forget to talk about it later. So let's look at page 145. We have the family of surfaces. Now, the family of surfaces works in a similar way as the family of curves that we did in the previous section. We're going to discuss one parameter family of surfaces. That is the surfaces that we have a collection, okay? And in each member of the family is defined with just one parameter. Okay, as an example let's consider the set of all tangent planes to a cone. So let's have a cone, like a ice cream cone, right? And then you can slap a tangent plane against it. And then, so all of them, imagine all the planes that's around this cone, and that is our family of surfaces for now. Now, to talk about this more carefully, let's consider the cone's equation from calculus 3 or 2 or 1, I don't know which one, is x1 squared plus x2 squared equals to x3 squared, or another way to put it is x squared plus y squared equal to z squared. If you were to type that into the Desmos 3D calculator, it'll show you a cone right there. Okay, and which I will show you in a moment. The parametric form of the cone is x1 u cosine v, x2 u sine v, and then x3 is just u. Okay, that's because x3 is like like the line, a straight line in any kind of when you look at it, okay? But anyway, so let's move on. Now, what is the tangent plane at a certain point, uv, in the parametric expression of this cone then? Then we are going to calculate the tangent plane. Let's first look at your book, page 107. That's when we learn how to do tangent planes. Now, right here, the tangent plane, okay, is x minus a, xu, xv determinant. And now, if you don't remember exactly how that worked out, don't worry about it, okay? We're just going to do this. So that is what I did. Now, first, we have our parametric representation of the cone. This is xu, right, xv. And then we did this many times back in those good old days on page 107. The tangent plane is the determinant of that thing. So let's write it out and then calculate it. And then I think I messed up something but once get out of there and don't mess up anything, then you end up being the whole determinant end up being this thing, this part being 0. Okay, so we only have this part left, and that is exactly what the book has. Where's the book? Let me find the book. Okay, so here is the tangent plane. Okay, so please do that yourself. Verify that this is indeed the tangent plane of some of the cone, and it's and as you can see, the tangent plane depends only on v. Okay, it just happened to work out that way. It doesn't care about u. So as v changes, that is the v is the angle of the cone going around. So as the angle changes, then we got the tangent plane already, because yeah, the plane goes that way. So u is not important in this case. So as a result, this particular equation then represents is an example of this family of surfaces. Okay, in this case, t v will stand for t, and then x1, x2, and x3 will be in here, right? And the whole thing equals to 0, and that would be our family of surfaces. All right, so next let's look at section 7.1. Oh, I forgot to show you the tangent plane for the cone. As you can see here, okay, there we have that's the parametric equation of the cone. The blue is the sample tangent plane, and the green line is the well, actually, I haven't talked about the green line yet. The green line is where the plane touches the cone, okay? But we haven't talked about that yet. So we'll talk about that in a little bit. Now, the definition 4, okay, on the bottom of page 145, we have the envelope. The envelope is defined very similarly to the envelope before. Now we have, the family has an envelope if for each t at t0, so we stop t, okay, at one point of t, but u can change, which means this becomes a curve. Now g of t at t0u is going to be on the surface of f, the f that we talked about a little earlier, the family of surfaces, again at t0. And along this curve, they're touching. That is, they have the same tangent planes as u changes. So then the curve is called, the curve has a name for it. It's called the characteristic curve, okay, on the next page, and of the surface f. Now let's, that's what I was showing you a moment ago, okay. If you look at this thing, there is then in this case, then we have the tangent plane, yeah, okay. The collection of all tangent planes then have a curve. Where's my curve? That's the green line. Okay, the curve only with yeah, I fix v at pi/2, so the curve only changes by u. So well, the curve happens to be a straight line here, and as you can see, the curve is where the tangent plane touches the surface, and the collection and as a result, the cone is the wrap, okay, of all the tangent planes, because all the tangent planes go around it, and so the cone. Oh, sorry, what did I say? Wrap? I mean envelope. Okay, to me, the word wrap sounds even better than envelope. But anyway, although this isn't exactly wrapping it on the outside, it's only wrapping on the inside. But either way, it's the envelope. So if I happen to say wrap, I mean envelope. So that is how that the definition works. So please read that yourself very carefully and make sure every sentence and every word makes sense. And with that, we will we will move on to theorem 7. Now, before we start on theorem 7, I want to refresh some old information that we haven't seen for a while. First, this is on page 67 of your book. Okay, pay attention to condition J, statement J, where it says that the plane through the point R with direction A for the normal has equation x minus r dot A equal to 0. That is, if your plane is x minus r dot A equal to 0, then A is the normal of the plane. I mean, yeah, of this plane. And I also wrote it here because I forgot to write it down in my notes. The next thing I want to mention is on page 107, I scanned it into the book. I mean, into my Kindle here, make it a little easier. Okay, so on page 107, we have a point where it says that the tangent plane of any surface, okay, let's say that surface is big F, x1, x2, x3 equal to 0. The tangent plane is x minus a dot grad F equal to 0, where grad F is this thing right here, okay, and that is partial F, partial x, y, and z. So when you, in other words, it's a vector function. So the tangent plane of any function is x minus a dot grad f. And because of that, as you can see from this equation, that also means the grad f is the normal of that tangent plane. So please remember that, okay, for the next few minutes. The grad f is, well, grad f is this thing, and more importantly, it is the normal. And the next thing I want to remind you of is theorem 6. This is on page 106. I just scanned it here so you don't have to look it up. If you have a parametric equation, all right, and then of a surface is what this is. This is a vector surface. Then the normal vector is going to be xu cross xv. This is the unit normal, so it divides by its own magnitude. But generally speaking, the normal vector, without worrying about the magnitude, is xu cross xv, where xu and xv are the partial derivatives of this thing. Okay, so that's theorem 6. So please remember that for a while. All right, so then with that, we should be able to start talking about theorem 7 on our current page, which is we're now on page 146. Now, the conditions, let's read the hypothesis of theorem 7. We have the family of surfaces, okay? And then there's a GTU, which is going to be the envelope. And then they are in C1 and so on, so we can take the partial derivatives without worrying too much. And then the grad F, which is the partial of against x, y, and z, not t. Okay, t is just the parameter for the family. But f itself, grad f, is not equal to 0. That is partial f against x, y, x1, x2, and x3, and so that's not 0, which just means that at least one of the partials are not 0. Okay, and that's all it takes. The other, if one of them is not 0, that's good. And the next condition is GT cross GU is not 0. That is required for our theorem 6 that I mentioned earlier. From theorem 6 on page 106, where the xu cross xv is not 0 is required for the theorem. So that as a result, being that we need that theorem in this proof, where that condition is listed here. And next, does the condition 4 means, well, if you stuff g into f, then it's identically 0. In other words, they have a common point, or I mean common surface curve there. Okay, and when you when t well, anyways, the point is, if you stuff it in there, it equals to 0. And then so they do share the, what that means is they share that, well, for each t equal to t0, I'm looking at definition 4 on the previous page, where it says that for each t equal to t0, the curve x equal to g t0 comma u lies on the surface of f. Okay, and so that means that's the same as condition 4. You plug it in, and it works out. E equals 0. And the fifth condition is the ones identical to our previous section, where the derivative against the fourth variable, the parameter, needs to be identically 0. Now, if these conditions all hold, specifically condition 4 and 5, okay, then the family has an envelope, and 4 and 5 is exactly how we're going to find the envelope, same as we did in the previous section. All right, so let's look at the explanation here. First, hypothesis 2 means that the partial derivatives are not all 0, okay, and then condition 4 means that we should note that in 4 and 5, the identities are true in both t and u. Okay, so the identity holds and for both variables. By 4, then of course it says that the curve lies on the surface because they plugged in and it all worked out. Now the next point is what we need to focus. Let's see, we have, okay, I have an illustration here to show you, all right. Let's see, I'll make it a little bigger. Is that big enough? Anyway, so here's the illustration. This is how I drew the illustration, but you can ignore that. Here's a surface F, okay? And F is x1, x2, x3, t0 equal to 0. So we're focusing on t0 at this point. And this is the blue surface is the surface x equal to gt comma u. Now the green line here is, so this is the surface, okay, t comma u, whereas the green line is at t0 and that's the characteristic curve, by the way. Yeah, and then so that is, and there's a vector here. What was the vector for? We'll talk about the vector later. I just want to show you, this is just a sample of what this theorem might be talking about. As you can see, there is the family, okay? That's just one member of the family, so it's T0. And this is the wrap, that's for all of them. And then we have some characteristic curve is where the two surfaces intersect at a tangent. Yeah. Okay. So let's look at the next part. The next part then is what we're doing. We are now going to do that. We are going to take the partial derivative of the family, okay, with respect to t, right? And then we're going to take it with respect to u as well, so that we can come up with some good stuff. And so that's what I did. Now, so please do this yourself as well. It's the same thing we've done many times before in chapter 1 or so. And so, but anyway, we plugged it in. This is equation 4. I plugged it in and wrote out all the variables so we can see it better. So we're taking derivative with respect to t. So very soon you realize equal to this thing. And specifically, remember that f4 equal to 0. Okay, that's hypothesis 5. So you can ignore that, which means we only have just the first 3 part, f1 g1 and f2 g2t, f3 g3t, which is the same as grad f dot gt equal to 0. Okay, because remember, grad f is the vector f1, f2, f3, right? So we got this thing right here. The next thing we're going to do is take the partial derivative of this equation now with respect to u. So then we get, with respect to u, then we get these 3 things, standard. Again, this is also grad f, but this time we have grad f dot gu equal to 0. Okay, what does that mean? If a vector dots 2 different vectors and are 0, that means the vector is perpendicular to the cross product, because the cross product is perpendicular to both vectors that is crossing. So which means that grad f is going to be parallel to gt cross gu. Okay, because due to the dot product being 0 in both cases. So it's parallel. If it's parallel, then what does that mean? Well, what is GT cross GU? GT cross GU, as we have mentioned in theorem 6, okay, GT, let's look at that again. GT cross GU, this is on page 106 of your book, is the normal, if you the parametric equations, when you take the partial derivative and cross it, that is the normal vector of your surface. So in other words, GT cross GU is the normal vector. Might not be unit normal, but normal. Okay, so if it's the normal vector, meaning that it's perpendicular, then we have grad f is perpendicular to GT cross GU. Now, but grad F is normal to the tangent plane, okay? And then GT cross GU is also the normal of the G surface. So which that means, and they are parallel, which means the two tangent planes are, well, the same, because they also go through the same point. That is, the two tangent planes are parallel, right? And they also cut through this, they also share a common point, which means the two tangent planes are the same. So, so that is the proof of theorem 7. Oh, I should show you that on my graph, okay, I picked a point, so let that be t, well, some point anyway, where t and u, x equal to gt and u, and where f shares the same point, where grad f is this arrow right here. You see, and so is GT cross GU. They have this. They are pointing the same direction, and then yeah. Anyway, so I thought that is so they both well, they're basically the same. There are actually two vectors here, but they point in the same direction and they're starting at the same point. But the two vectors might not be the same length, okay? But that doesn't matter to us because we only care that the tangent, which direction is the tangent plane facing. So then if they're parallel, then the tangent planes are the same. So next, let's look at the bottom of page 146. We have the way to actually find envelopes is then we take the F, okay, and the F4, and then and solve them like simultaneous equations. Now and at any fixed t, the intersection is the curve of the two, the curve, the characteristic curve, I mean, the one that's mentioned up here, okay? And the locus are all the curves. Locus means the entire collection of them, okay? As the curve moves along, it spins out, it sweeps a surface, and that surface is, as t varies, will be the desired envelope. So basically, to find the envelope, we need to figure out how to get rid of t, and so we have an equation of just x1, x2, x3, which you can type it into Desmos calculator, and it'll pop out the equation. I mean, it pop out the graph right in your face, okay? So it's very nice that way. Let's go back to our example of the cone. Now this is the collection of the tangent planes for the cone, right? And then we take partial derivative with F4. In this case, V stands for t, so taking partial derivatives with respect to V then gives us this equation. And then a quick manipulation of these two things, if you stare at it long enough, you square both sides, then you quickly notice the x1 squared, which is that x3 squared, okay, which is this thing, is going to be equal to x1 squared plus x2 squared. You just, well, you square both sides and then add them up and this will show up, okay? You can do it in your head because the sine and cosine and being squared, and there's a negative sign here which cancels stuff out. So this thing, yeah, this can do it. You can do this very quickly. So please do this yourself and be sure to prove theorem 7, go over it yourself to make sure that you understand every last bit of it, okay, as the rest of the book. So, so that's that. I will finish this section in the next video.